Hello, and welcome to this FMSP Core Prerequisites video. These videos are designed to help you get ahead with independent study of the A2 core, ready to develop the skills in A2 Further Pure modules. You need to be confident with all of these ideas before starting this video, so if necessary, watch the first two videos in this section and do some appropriate consolidation work first. You'll need these materials to hand, so pause the recording now and go and get everything together. And make sure you've set aside enough time to do the questions as well as watch the video. This is what we'll be covering in this video. We can think of the vector equation of a straight line as being instructions to get to any point on the line. First we need to get on the line from the origin O, and we'll use a vector which we'll call A to get onto this line. Then we need to move along the line to the right point, so we need a vector in the direction of the line. It can go either way, and it can be any size, but it needs to go along the line. Let's do an example to see how this works. First of all, from the origin, I need to use the vector 2, 3 to get to the point 2, 3, which is on the line. I can then use the vector 3 minus 4 to move along the line. That's the vector which gets me from 2, 3 to 5 minus 1. I can use any multiple of that vector and it will take me to different points. So the equation of the line is the position vector of a point on the line is 2, 3 plus some multiple of 3 minus 4. So this Greek letter lambda just means that we can take any multiple that we like of that direction vector. So this was the vector equation that we had, and we can use it to see if particular points are on the line. So does the point 8 minus 5 lie on the line? Well, to start with, we'll use the x-coordinate to find lambda. So the x-coordinate is 2 plus 3 lambda, and that needs to be equal to 8. That means that lambda must be 2. If lambda is 2, then the y component is 3 minus 4 lambda. That's 3 minus 8 is minus 5. So yes, 8 minus 5 lies on the line. What about minus 1 minus 1? If 2 plus 3 lambda is equal to minus 1, so if the x-coordinate is right, then lambda must be equal to minus 1. But does this value of lambda give me minus 1 for the y-coordinate? If lambda is equal to minus 1, then the y-coordinate is 3 plus 4, which is 7, not minus 1. So minus 1 minus 1 is not on the line. The vector equation of a line is not unique for that particular line. We could have used the vector 5 minus 1 to get onto the line instead of 2, 3. And instead of 3 minus 4, we could have done minus 3, 4 to move along it. That would have given us the equation r equals 5 minus 1 plus lambda minus 3, 4. And we've got lots of choice very easily for that direction vector. I could have used minus 6, 8 or minus 9, 12. Generally speaking, it's a good idea to use the simplest one. We can use I and J notation for this, as we've used elsewhere. Personally, I find it easier to work in column vectors, so whatever the question looks like, I will always translate into column vectors. But you need to be able to read in I and J notation, and you need to be able to put your final answer back into that notation if that is what the question is asking for. So in this example, my direction vector is here 2i plus 3j. So if I've got a line which is parallel to that, it must have the same direction vector. So looking at this one, that's got a different direction vector. This one, however, 4i plus 6j, is just a multiple of 2i plus 3j, and so will do quite nicely as the direction vector. So that one is parallel. And the final one, the direction vector I plus j, is not parallel, so that line isn't parallel. We can work in 3 dimensions using I, j and k. Here I'm given the equation of a line and asked to show that the point is on the line. So I'm going to start by rewriting my vector equation in columns. And then I'm going to set it equal to the position vector of the point P, 3 minus 14, 15. That gives me 3 simultaneous equations. If P lies on the line, then these equations must be true for the same value of lambda. 1 minus 3 lambda is 14, 5 plus 2 lambda is 15. So, equation 1 tells me that lambda must be equal to 5. I now need to check both of the other points, components, to make quite sure that both of them satisfy. So 1 minus 3 lambda, that's 1 minus 15, which is minus 14, which is what I wanted, and 5 plus 2 lambda is 5 plus 10, which is 15, which is the z component. So the point is on the line. It's really important that you check that all the components work with the calculated value of lambda in order to make sure that you really have shown that the point lies on the line. Okay, time for you to have a go. Pause the video and try this one before watching the solution. Right, the first thing we need is a vector along the line. So AB is to get from A to B, minus 2 to 3 is 5, and 4 to 7 is 3. So that means that a vector equation for the line has to have that direction vector, and that is B, and you can see that the first vector, minus 2, 4, is the position vector of the point A, so that gets us onto the line okay. Right, pause the video again and try this one. Okay, I need a vector equation which is parallel to this line, which means it needs to have this vector as its direction vector, or some multiple of it. Well, that counts out A and B and D, so I'm only looking at C, and I'll double check, and the point that gets me, the vector that gets me onto the line, corresponds to the point that I need, 2 minus 1, 0. So the answer is C. Okay, this is stating the obvious, but it gives us a strategy for checking whether 2 lines intersect. Here are 2 lines. I'm asked to show that they intersect. We need both x and y to be the same. So I need the x component, that's 1 plus lambda on the first line, to be equal to 11 plus mu on the second. And for the same values of lambda and mu, I need minus 3 plus lambda to be equal to 1 minus 2 mu. 1 and 2. If I do equation 1, take away equation 2, then I get 4 equals 10 plus 3 mu. And from that I get that 3 mu is 6 and mu is minus 2. I'm then going to substitute for mu in 1 and 2. Now, I'm sure your teachers have always told you that you should check in both equations to make sure you haven't made any mistakes. But here we don't actually know whether or not the equations are simultaneous. That's what we're being asked to show. So we need to not just do it in our heads, but actually demonstrate that the equations are simultaneous and we get the same value of lambda from both of them. So for equation 1, 1 plus lambda is 11 plus mu, so that's 11 minus 2. So 1 plus lambda is 9, so lambda is 8. And equation 2 tells me that minus 3 plus lambda is 1 minus 2 mu. So that's 1 plus 4 is 5, so that also tells me that lambda is equal to 8. So the lines intersect. Remember, we don't know the equations are simultaneous, so we must check both equations. Now, we could have explained immediately that they intersect simply by looking at the direction vectors. The direction vectors are not parallel. So the lines are not parallel, so they must intersect. But, of course, if they ask you to find the point of intersection, you'll still need to do the same work. And if we're working in 3 directions, then non-parallel lines don't necessarily intersect. So we have 3 things to check. Here we're asked to show that the lines are skew lines. So we're asked to demonstrate that our simultaneous equations are not going to be simultaneous. So x components 2 plus 0t is minus 3 plus 5s. 0 plus 2t is 0 plus 4s. And minus 1 plus 3t is equal to 2 minus s. Equation 1 tells us that s is equal to 1. If s is equal to 1, then equation 2 tells us that t is equal to 2. However, for equation 3, the left-hand side is minus 1 plus 3 lots of t, that's 6, which is 5. And the right-hand side is 2 minus s, 2 minus 1 is 1. So the lines do not intersect. We can see that they're not parallel because the direction vectors are not the same, so the lines are skew. Okay, pause the video and try this one yourself. Right, let's see what we've got. For my own preference, I like to write these as column vectors first. There's less writing then, it's easier to see what's going on. So equation L, sorry that's a colon, not an equal sign. Equation L, R equals 3, 0, 1 plus T 1 minus 1, 2. And equation M, R is equal to minus 2, 3, 1 plus S 2 minus 1, 1. And for equation N, R is equal to 4, 1, 3 plus are 1 minus 3, 2. Okay, I need to check the line L with each of the lines L, M and N. So we'll start with L and M, and that gives me 3 plus T equals minus 2 plus 2S, minus T equals 3 minus S, and 1 plus 2T equals minus 1 plus S. If I add equations 2 and 3, then I get 1 plus T equals 2, and that means that T equals 1. Equation 1 then tells me that 3 plus 1 is equal to minus 2 plus 2S. So that tells me that 2S is 6 and S is 3. However, equation 2 tells me that minus 1 is equal to 3 minus S, which would give me that S was equal to 4. So my equations are not simultaneous, and I don't even need to bother checking 3. Then I need to check L and N, and that gives me 3 plus T equals 4 plus R, minus T equals 1 minus 3R, 1 plus 2T equals 3 plus 2R. If I add now equations 1 and 2, that gives me that 3 is equal to 5 minus 2R, which tells me that R is equal to 1. From equation 1, 3 plus T is equal to 4 plus 1, which tells me that T equals 2. Equation 2 tells me that minus T is equal to 1 minus 3, which again tells me that T equals 2. And from equation 3 I get 1 plus 2T equals 3 plus 2, which is 5. So 2T is 4 and T is 2 again. So my line, the lines L and N do intersect, but L and M do not intersect. And that's option D. Okay, you need to do plenty of practice now. Don't skimp on this. You've got to do it sometime, and now is the best time to do it. I hope you found this video useful. I look forward to you joining me for the final video on the scalar product. Goodbye.